We'll start in a minute. Today we will cover section 8.2, graphs of the other trigonometric functions, and then after that we'll go over the test 1 review. Test 1 is on Monday from 11 to 11:50. I sent an email and indicating that you can start as early as 10:45 a.m. Okay, the first thing we'll do in section 8.2 is analyze the graph of y equals tangent of x. Recall that tangent of x is sine of x divided by cosine of x. And cosine of x is 0 for odd multiples of pi over 2. So odd multiples of pi over 2, a couple of negative ones, negative 3 pi over 2, negative pi over 2, positive pi over 2, 3 pi over 2, and so on. So since cosine of x is 0 for those values, the tangent of x is undefined for odd multiples of pi over 2 because division by 0 is undefined. So consequently, the graph of y equals tangent of x in the xy plane has vertical asymptotes at those odd multiples of pi over 2. Also recall that y equals tangent of x is an odd function, since tangent of negative x equals sine of negative x divided by cosine of negative x. But in the numerator, sine of negative x is negative sine of x. And in the denominator, cosine of negative x is just cosine of x, because cosine of x is even. So the tangent of negative x equals the negative tangent of x. So that means the graph of y equals tangent of x is symmetric with respect to the origin, since it's an odd function. Okay, before graphing one period of the y equals tangent of x function, we'll evaluate the tangent of x at several input values. When x is negative pi over 2, well, as we just mentioned, tangent of negative pi over 2 is undefined because the denominator is 0. Division by 0 is undefined. Tangent of negative pi over 3, well, that's sine of negative pi over 3 divided by cosine of negative pi over 3. And so that's negative square root of 3 over 2 divided by 1/2. So we get negative square root of 3. Tangent of negative pi over 3 is negative square root of 3. Tangent of negative pi over 4, Well, that's the same as sine of negative pi over 4, which is negative square root of 2 over 2. And the denominator cosine of negative pi over 4 is equal to cosine of pi over 4, which is positive square root of 2 over 2. So tangent of negative pi over 4 is equal to negative 1. Okay, a few more. Tangent of negative pi over 6, that's equal to sine of negative pi over 6 divided by cosine of negative pi over 6, or negative 1/2 divided by the square root of 3 over 2. That simplifies to negative 1 over the square root of 3. Tangent of 0 is sine of 0 divided by cosine of 0. Sine of 0 is 0. Cosine of 0 is 1. So tangent of 0 is 0 divided by 1, or 0. Okay, then the tangent of pi over 6, we can use the fact that tangent of negative pi over 6 is equal to negative 1 over the square root of pi to help us. Tangent of pi over 6 is just positive 1 over the square root of 3. And tangent of pi over 4 is equal to 1. Here we can use the fact that tangent of negative pi over 4 equals negative 1 to get tangent of pi over 4 equals positive 1. And tangent of pi over 3 is equal to the square root of 3. If we look at tangent of negative pi over 3 equals negative square root of 3, then we can make that conclusion. And then tangent of pi over 2. Sine of pi over 2 is 1 in the numerator. Cosine of pi over 2 is 0 in the denominator. So 1 divided by 0 is undefined. So tangent of x is undefined at x equals pi over 2. Okay, so now we can graph a period of the sine function. We have vertical asymptotes at negative pi over 2 and pi over 2, because tangent is undefined at tangent of x is undefined at negative pi over 2 and pi over 2. So we have vertical asymptotes. So one strategy in graphing a tangent function is to divide the period into 4 parts. Notice that the period of this tangent function, y equals tangent of x, is pi, because from negative pi over 2 to pi over 2 is pi. So between negative pi over 2 and 0, we have negative pi over 4. And halfway between 0 and pi over 2 is pi over 4. And so the idea is, if we can plot, or if we use the input values negative pi over 4, 0, and pi over 4, we can plot 3 points for y equals tangent of x. And then through those 3 points, we can sketch the rest of the graph. Okay, so when x is negative pi over 4, tangent of negative pi over 4 is negative 1. So I'll write -1 here and +1 there. Okay, so we'll plot the point -π/4, -1 here. And then when x is 0, tangent of 0 is 0. So we have this point on the graph. And then tangent of π/4 is +1. So that's enough to get a reasonable graph for tangent of x on this interval between -π/2 and -π/2 and π/2. So I'll try not to botch this too much. So the graph looks something like this. Okay, let's fill in this other information. The period of y equals tangent of x is pi. We didn't have a phase shift on this one. This is just one period of the y equals tangent of x function. If we graphed another one, we would just go from π/2 to pi to 3π/2. And then at 3π/2, we have another vertical asymptote. But the graph in this period has the same pattern as this one over here. So we have these points. So my graphs won't look the same, but they're supposed to be the same. If you want a better picture of the tangent function, you could look in the textbook. But anyway, the domain is all real numbers except when x is an odd multiple of π/2. So I'll just say that x does not equal 2n minus 1 times π/2. The stretch factor is 1 because it's y equals 1 times tangent of x. For this graph, we don't have a vertical shift. The range of tangent, y equals tangent of x, is all real numbers, -∞ to +∞. Okay, that's the graph of y equals tangent of x. Okay, we'll consider graph variations of y equals a times tangent of bx, b times x. Okay, the period of, since we have b times x, the period is pi divided by the absolute value of b. This one has no phase shift. The domain is any x value that makes b times x an odd multiple of π/2. So we could say that x does not equal well, I have a blank right now. I'll fill this in a little bit later. The stretch factor is the absolute value of a, and there is no vertical shift. And the range is -∞ to +∞. Okay, like we did with sine and cosine, we can look at this argument bx and we can say negative pi over 2 has to be less than b times x, which is less than pi over 2. So negative pi over 2 times b is less than x, which is less than pi over 2 times b. Okay, so I can use this to help me for the domain. X cannot be equal to, well, I know negative pi over 2 times, in general, the absolute value of b, and then other multiples of that. Okay, let's look at this particular function, y equals 1/2 tangent of pi over 2x. So let's find the period. The period can be found by dividing pi by pi over 2. This is the equivalent to pi over 1 times 2 over pi. The pi's cancel, so we get a period of 2. An alternative to that, as we did up here, so if we write negative pi over 2 is less than pi over 2x, which is less than pi over 2, and then divide all 3 parts by pi over 2. Negative pi over 2 divided by pi over 2 is negative 1. Pi over 2 times x divided by pi over 2 is just x. And pi over 2 divided by pi over 2 is 1. So the length of this interval is 2, so the period is 2. Here we don't have a phase shift. And the domain is every real number except the odd integers. So x does not equal 2n minus 1 for any integer n. The leading coefficient is 1/2, so we don't really have a stretch factor, we have a compression factor. The compression factor is 1/2. We don't have a vertical shift, and the range is negative infinity to positive infinity. Okay, so let's sketch 2 or 3 periods for the y equals 1/2 tangent of pi over 2x. So we have vertical asymptotes at the odd integers. Okay, I'll sketch in the vertical asymptotes at the odd integers. Okay, so we have 0 right in the middle. So if we look at the period between -1 and 1, we'll subdivide this into 4 parts again. So when x is -1/2, 0, and +1/2, we'll evaluate y equals 1/2 tangent of pi over 2 times x at each of those 3 values. We'll plot those values and then draw the graph through those three points. Okay, so when x is -1/2, pi over 2 times -1/2 is -pi over 4. And tangent of -pi over 4 is -1, and 1/2 times -1 is -1/2. So here is where 1 is, here is, or sorry, -1, and here is where +1 is. So when x is -1/2, the output is also -1/2. So about right here. When x is 0, pi over 2 times 0 is 0. Tangent of 0 is 0. 1/2 times 0 is 0. So we have this point on the graph. And then when x is 1/2, pi over 2 times 1/2 is pi over 4. Tangent of pi over 4 is 1. 1/2 times 1 is 1/2. So we have this point. And then tangent will have this shape similar to the last graph that we did. And the other periods will also follow the same pattern between 1 and 3. So at 1.5, the output is 1/2. At 2.5, the output is 1/2. So here's the period between 1 and 3. And I'm sure you get the idea, but we'll do one more. At -2 and 1/2, we have an output of -1/2. At -2, we have an output of 0. And at -1.5, we have an output of 1/2. So there is our third period. Okay, next page, we'll look at the general setting. Okay, so if we have y equals a times tangent of bx minus c plus d, the period is pi divided by the absolute value of b. The phase shift is c over b. So on here, I'll just say the domain is bx minus c does not equal an odd multiple of pi over 2. The stretch factor is the absolute value of a. If this number is greater than 1, then it stretches the graph vertically. If the absolute value is between 0 and 1, then it compresses the graph vertically. The vertical shift is d units. If d is positive, then the shift is upward, and if d is negative, The shift is downward. And the range is all real numbers. Okay, so in this function, y equals -2 times tangent of pi times x plus pi. The period is pi divided by the coefficient of x, pi. So the period is just 1. The stretch factor is the absolute value of -2, which is 2. The vertical shift, there isn't one on this one. And the phase shift is -pi over pi, or -1. And the domain, we can say pi x plus pi does not equal an odd multiple of pi over 2. Okay, so I'm going to, again, use the argument pi x plus pi. I'm going to write for that middle interval, -pi over 2 is less than pi x plus pi, which is less than pi over 2. And then solve this inequality for x. So first we'll subtract pi from both sides. -pi over 2 minus pi is -3/2 pi, or -3 pi over 2. That's less than pi times x. And then on the right-hand side, pi over 2 minus pi is -pi over 2. And then when we divide each of the 3 parts by pi, -3 pi over 2 divided by pi is -3/2. Pi x divided by pi is x. And -pi over 2 divided by pi is -1/2. Okay, so we can see that the length of this interval is 1. If you write -1/2 minus -3/2, you get 1. So the period is 1. And we have a vertical asymptote at -3/2 and also at -1/2. The range is all real numbers. So let's go ahead and sketch the graph. So one of our vertical asymptotes is at x equals -1/2. There's -1, and then -3/2. So I'll sketch in the vertical asymptotes. So if we use the strategy that I suggested, divide this interval from -3/2 to -1/2 into 4 parts. The middle point is -1. And halfway between -1.5 and -1 is -1 1/4, or -5/4. And halfway between negative 1/2 and negative 1 is negative 3/4. So if we can plot the points that correspond to negative 5/4, negative 1, and negative 3/4, we'll plot those points and then draw the graph, one period of the tangent function. Okay, so on this one, I'll use a chart for those input values. The input values are negative 5/4, negative 1, and negative 3/4. And then I'll rewrite what the y value is. Y equals negative 2 times the tangent of pi times x plus pi. Okay, so when x is negative 5/4, pi x plus pi, so pi times negative 5/4 is negative 5/4 pi plus pi is negative pi over 4. So tangent of negative pi over 4 is negative 1, and negative 2 times negative 1 is positive 2. When x is negative 1, then we have the tangent of pi times negative 1 plus pi. Pi times negative 1 is negative pi plus pi is 0. Tangent of 0 is 0, and negative 2 times 0 is 0. And then when x is negative 3/4, replace x with negative 3/4, we have negative 3/4 pi plus pi, which is pi over 4. Tangent of pi over 4 is 1. Negative 2 times 1 is negative 2. So we'll plot those three ordered pairs. Let's see, I need so the two scales on the x-axis and the y-axis aren't exactly the same. Okay, but when x is negative 5/4, the output is positive 2. When x is negative 1, the output is 0. And when x is negative 3/4, the output is negative 2. So we have this graph, roughly. Okay, moving on. Now we'll discuss graphs of y equals secant of x and y equals cosecant of x. We saw a bunch of those examples yesterday, but those are more formally covered in this section 8.2. Since secant of x is equal to 1 over cosine of x, secant of x is undefined for odd multiples of pi over 2. And so the graph of y equals secant of x has vertical asymptotes at odd multiples of pi over 2. The reason is since cosine is equal to 0 when x is a odd multiple of pi over 2, 1 divided by 0 is undefined, so we have vertical asymptotes. And as we saw yesterday, the graph of y equals cosine of x can be used to graph y equals secant of x. Okay, so yesterday we saw how to graph y equals cosine of x. So if we go between 0 and pi, and then, 0 and 2 pi, and subdivide the interval into 4 equal parts. So we go from 0 to pi over 2, to pi, to 3 pi over 2, to 2 pi, and we'll extend to the left to negative pi over 2 also. So when graphing cosine of x, cosine of negative pi over 2 is 0. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. Let's extend the graph a little further. So we also include 5 pi over 2. Cosine of 5 pi over 2 is 0. Okay, so we'll sketch in the cosine function. So we just have 1.5 periods of the cosine function. And we're going to use the graph of y equals cosine of x to graph its reciprocal, y equals secant of x. So y equals secant of x has vertical asymptotes at the odd multiples of pi over 2. And so y equals secant of x between negative pi over 2 and pi over 2 will look something like that. Between pi over 2 and 3 pi over 2, the graph looks something like this. And between 3 pi over 2 and 5 pi over 2, the graph of y equals secant of x looks like that. So the red graph is y equals secant of x. Okay, so if you ever had to draw one period of y equals secant of x, well, you could do it as long as you included an interval of length 2 pi. So you could go from negative pi over 2 to 3 pi over 2. That is one period. But if you go from 0 to 2 pi, then you would just have that part of the graph. Okay, so we'll go through the same kind of thing with graphing the cosecant of x function. Since cosecant of x equals 1 divided by sine of x, cosecant of x is undefined for integer multiples of pi. So the graph of y equals cosecant of x has vertical asymptotes at integer multiples of pi. And then the graph of y equals sine of x can be used to graph y equals cosecant of x. So if we sketch a graph of y equals sine of x, the period of y equals sine of x is 2 pi. So if we subdivide the interval from 0 to 2 pi into 4 parts, so let's start from 0 to 2 pi first. Sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. So one period of sine between 0 and 2 pi will look like that. And we can sketch in one other period of sine over here between negative 2 pi and 0. And then to graph y equals cosecant of x, well, it will have vertical asymptotes at the integer multiples of pi. So at negative 2 pi, at negative pi, at 0, at pi, and at 2 pi. So the graph of y equals cosecant of x between negative 2 pi and negative pi will look something like this, between negative pi and 0, like that, and so on. Okay, so y equals cosecant of x is the graph in red. Okay, since I won't do these two problems, I'll just mention a couple of things. If you want to graph one period of y equals 2 times cosecant of 2x minus pi, then just graph y equals 2 times sine of 2x minus pi, and then plot the vertical asymptotes, and then sketch in the graph of y equals 2 times cosecant of 2x minus pi. I'll just write, use the graph of y equals 2 times sine of 2x minus pi, and do what we did on the other examples to get a graph of the cosecant function. And a similar comment for this one. In order to graph y equals negative secant of x plus pi over 4, you can use the graph of y equals negative cosine of x plus pi over 4. So graph one period of y equals negative cosine of x plus pi over 4, sketch in the vertical asymptotes, and then graph y equals negative secant of x plus pi over 4. Okay, we'll talk about the cotangent of x function. So if you know how to get started with the cotangent function, then you can use what we talked about when graphing y equals tangent of x and apply those concepts to y equals cotangent of x. So cotangent of x is cosine of x divided by sine of x. And since sine of x is equal to 0 for multiples of pi, cotangent of x is undefined for integer multiples of pi. So that means that the graph of y equals cotangent of x in the xy plane has vertical asymptotes at the integer multiples of pi. So we also know that y equals cotangent of x is an odd function because cotangent of negative x equals the negative of cotangent of x. So that means the graph of y equals cotangent of x is symmetric with respect to the origin. Okay, we'll fill in a few values for y equals cotangent of x. When x is 0, cotangent of 0 is undefined. Remember, the denominator sine of 0 is 0 when x is 0. So cotangent of 0 is undefined. Cotangent of pi over 6, well, that's the square root of 3. Cotangent of pi over 4 is positive 1. Cotangent of pi over 3 is 1 over the square root of 3. Cotangent of pi over 2 is 0 because in the numerator, cosine of pi over 2 is 0. In the denominator, sine of pi over 2 is 1. 0 divided by 1 is 0. And then for x equals 2 pi over 3, this is in the second quadrant, so cotangent is negative. And it's negative 1 over the square root of 3. At 3 pi over 4, this is also in the second quadrant. So cotangent of 3 pi over 4 is negative 1. And cotangent of 5 pi over 3 is negative square root of 3. And cotangent of pi is negative 1. Sorry, it's undefined. The denominator, sine of pi, is 0, so division by 0 is undefined. Okay, we'll sketch one period of y equals cotangent of x. And this will be from 0 to pi. So on the the y-axis, we have a vertical asymptote from 0 to pi. We have vertical asymptotes there. We'll subdivide the interval from 0 to pi into 4 parts. Okay, then we'll plot the primary points. So when x is pi over 4, cotangent of pi over 4 is 1. when x is pi over 2, cotangent of pi over 2 is 0. And when x is 3 pi over 4, cotangent of 3 pi over 4 is negative 1. So the graph will have this shape, roughly, for that period. Okay, so for y equals cotangent of x, the period is pi. On this one, we don't have a phase shift. The stretch factor is 1. There's no vertical shift. The domain x does not equal integer multiples of pi. And the range is from negative infinity to infinity. Okay, so that concludes the section 8.2 material. We'll look at the test 1 review sheet next. Okay, the test 1 review sheet. This covers chapter 7 material. So this one convert from degrees to radians. So we multiply 165 degrees by pi over 180 degrees. 15 goes evenly into 180 and 165. So 15 times 11 and 15 times 12, the 15s cancel. So this is just 11 pi over 12. 27 degrees multiplied by pi over 180. Well, for this one, 9 goes into 27 3 times, and 9 goes into 180 20 times. So 3 pi over 20 is what I get. And then 72 degrees, multiply that by pi over 180. So let's see, 18, no, even higher than that, 36. 36 goes into 72 twice, and 36 goes into 180 5 times. So this is 2 pi over 5 radians. The next part, find coterminal angles between 0 degrees and 360 degrees, or between 0 and 2 pi radians as appropriate. So this one is in radians. Notice that 13 pi over 6 is 12 pi over 6 plus pi over 6, or 2 pi plus pi over 6. So pi over 6 is coterminal with 13 pi over 6. 395 degrees. Well, this is equivalent to 360 degrees plus 35 degrees. 360 degrees is one rotation, so a coterminal angle is 35 degrees. This next angle is outside of, it's a negative one outside of the range. So to find a coterminal angle, we could just add 2 pi, negative 3 pi over 2 plus 2 pi. and we get pi over 2. So pi over 2 is coterminal with negative 3 pi over 2. The next exercise, find the reference angles. Negative 3 pi over 4. Well, if we were to draw this as a winding angle, negative 3 pi over 4, we move clockwise. So there's negative 3 pi over 4. And we're pi over 4 radians short of 1/2 of a revolution. So the reference angle is pi over 4. 285. So counterclockwise. So if we go this far, that's 270. So 15 degrees more is that angle. So this is 285 degrees. And the reference angle is 75 degrees. Okay, the next one, 4 pi over 5. So 4 pi over 5 is less than pi by 1/5 pi. So we get about this far, 4 pi over 5. And the reference angle is pi over 5. Okay, the next part, given central angle theta and radius r, find the arc length and sector area. So in the middle here, I'll remind you of the arc length formula. So the arc length S is equal to the radius times the measure of the central angle in radians. And the sector area, I'll call it A sub theta. That's equal to 1/2 times the radius squared times theta measured in radians. Okay, so for this one, the arc length F is equal to 14 times pi over 7, or 2 pi inches. We'll include the units when appropriate. And then the area, A sub theta, is equal to 1/2 times 14 squared times pi over 7. Do the arithmetic, we just get 14 pi square inches. Okay, for this one, if theta is 2 radians and the radius is 5 feet, then the arc length is 5 times 2, or 10 feet. And the area is 1/2 5 squared times 2. Simplify that, we just get 25 square feet. Hey, make sure you know how to do those on Monday. Okay, number 5, a wheel with a radius of 8 inches rotates at 15 degrees per second. Find the linear speed v, the angular speed in revolutions per minute, and also the angular speed in radians per second. Well, let's work on the angular speed in radians per second first. So if we convert from degrees to radians, then we'll know what the angular speed is in radians per second. So convert 15 degrees to radians, multiply 15 degrees by pi over 180 degrees. 15 goes into 180 12 times, so this simplifies to pi over 12 radians. And so the angular speed in radians per second is pi over 12 radians per second. That's the third part. I think the next thing that's easiest to do is to find the linear speed v. If you remember that the linear speed v is just the radius multiplied by the angular speed. And we know what the radius is, and we now know what the angular speed is in radians per second. So the linear speed is 8 times pi over 12 inches per second. If you want to reduce the fraction, you can. This is a perfectly fine test answer, but if you want to write it as 2 pi over 3 inches per second, you can do that. Okay, now we want to find the angular speed in revolutions per minute. So to find the revolutions per second, we'll do that first. Revolutions per second. We divide the linear speed that's in radians per second by 2 pi. So pi over 12 divided by 2 pi. This will be revolutions per second. So let's see, this pi over 12 times 1 over 2 pi. So we just get 1 over 24 revolutions per second. Okay, well, an RPM is a revolution per minute. So we just need to convert 1 over 24 revolutions per second to revolutions per minute. We can do that. Revolutions per minute is equal to 1 over 24 times revolutions per second. We just need to convert to minutes. So every second, I should say every minute, has 60 seconds in it. So I multiply this by 60 seconds over 1 minute so that the seconds units cancel. And then we're just left with 1 over 24 times 60. 12 goes into 24 and 60 evenly. So we get 5/2 revolutions per minute. Sorry. Revolutions per minute. Or you could write 2.5 revolutions per minute. Okay, the next page, 7.2. Okay, in a right triangle, the measure of the smallest angle is alpha. The lengths of the sides of the right triangle are 5, 12, and 13 inches. Evaluate all 6 trigonometric functions for alpha. Okay, so one thing we should be able to do is, from geometry, we can import what we know from geometry. If the smallest angle of a right triangle is alpha, we know that in geometry we learned that the side of a triangle that is opposite of the smallest angle will be the side with the shortest length. So of the lengths 5, 12, and 13, the side opposite of the smallest angle, whose measure is alpha, has to be 5. We also know that in a right triangle, the hypotenuse is the longest side, so we have 13 for the hypotenuse and 12 for the length of the side that's adjacent to alpha. Okay, so that's enough information. We can write down sine of alpha is 5 over 13, the opposite over the hypotenuse. Cosine of alpha is 12 over 13, the adjacent side over the hypotenuse. Tangent of alpha is opposite over adjacent, 5 over 12. You can get the same number if you divide sine of alpha by cosine of alpha. And then the reciprocal functions, cosecant of alpha is the reciprocal of sine, or 13/5. Secant of alpha is the reciprocal of cosine, so that's 13 over 12. And cotangent of alpha is the reciprocal of tangent, so it's 12 over 5. Okay, for the next exercise, find the missing angles. Cosine of pi over 2 minus beta equals sine of beta. So remember the cofunction identities. So cosine of pi over 2 minus beta. This is literally one of the cofunction identities, sine of beta. But it also works the other way. I'll up here I'll write that sine of pi over 2 minus beta equals cosine of beta. So for this one, we have inside knowledge already because we know that sine of pi over 3 is the same number as cosine of pi over 6. But we could use this cofunction identity in reverse. So sine of pi over 3 is equal to the cosine of pi over 2 minus pi over 3. So that's equivalent to 90 degrees minus 60 degrees, which is 30 degrees, or pi over 6. So sine of pi over 3 is equal to cosine of pi over 6. The cofunction identities also apply to cotangent and tangent. So, in other words, tangent of pi over 2 minus beta is equal to cotangent of beta. We already know that cotangent of pi over 4 equals 1 and tangent of pi over 4 equals 1. But we can use this identity just to show that if beta is pi over 4, tangent of pi over 2 minus pi over 4 is equal to cotangent of pi over 4. But pi over 2 minus pi over 4 is just pi over 4. Okay. Number 3. One acute angle in a right triangle measures pi over 12 radians, and the shortest side is 18 inches. Find the lengths of the other two sides. Well, pi over 12 radians, we can tell by looking that it's smaller than pi over 4. So this has to be the smallest angle. So in a right triangle, we'll label the smallest angle pi over 12. And consequently, the shortest side is opposite of the smallest angle. So this side is 18 inches. And we want to find the length of the other two sides. So I'll label the hypotenuse capital H and the other side capital A. There are a number of ways we can go about finding the values of A and H. Some might be easier than others. One thing you can do, you can write sine of pi over 12 equals opposite over hypotenuse, so 18 over H. And when you solve this for H, you get H equals 18 divided by sine of pi over 12. Hey, for a test answer, this is perfectly fine. Pi over 12 is not a special angle, so sine of pi over 12 is something that we would usually rely on a calculator to give us a decimal approximation for. So that's the answer for H. And then to find A, well, we have options, but one option is just to use tangent. Tangent of pi over 12 equals 18 over A. And when you solve this for A, you get A equals 18 divided by the tangent of pi over 12. Okay, in the next example, next problem, from a nest in a tree, an owl observes a hiker at an angle of depression of 30 degrees. If the hiker is 210 feet from the base of the tree, find the height of the owl's nest. Okay, so if we have suppose here's the owl's nest. And the hiker is 210 feet from the base. from the base of the tree, the angle of elevation is 30 degrees. Sorry, I said that wrong. The angle of depression, that's this angle. Remember, don't forget, you could do this problem incorrectly if you put the angle of depression in the wrong place. So it's from the horizontal to the downward line of vision. That's the angle of depression. That's 30 degrees. Well, you might remember from geometry, if you have two parallel lines, then alternate interior angles are congruent. So from the hiker's perspective, looking to the owl's nest, we have an angle of elevation of 30 feet, 30 degrees. So we can say, to find the height or how high the owl's nest is, we can use tangent of 30 degrees equals h divided by 210, or h equals 210 times tangent of 30 degrees. Well, we do know that tangent of 30 degrees is 1 over the square root of 3. So this is measured in feet. So we could say h is equal to 210 divided by the square root of 3 feet. Okay, the next sheet for 7.3 problems. Determine if the ordered pair 2/3, comma, square root of 5 over 3 is a point on the unit circle. Okay, so the unit circle is a circle of radius 1 centered at 0, 0. So radius 1. So if you pick any point anywhere on the circle, x, y, what has to be true? Well, since this is the unit circle, the equation for that circle is x squared plus y squared equals 1. So if an ordered pair is on the circle, then it has to satisfy this equation. So we just substitute x with 2/3, so we have 2/3 squared. We add that to the y coordinate squared, and we want to know if that equals 1. So it'll only take a couple of seconds to figure this out. So when you square 2/3, you get 4/9, and when you square the square root of 5 over 3, you get 5/9. So 4/9 plus 5/9 is 9/9, which is equal to 1. So the answer is yes, that ordered pair is on the unit circle. Okay, next problem. If sine of t equals negative 3/5 and t is in the third quadrant, find cosine of t and tangent of t. Okay, if it's in the third quadrant, So third quadrant, well, we know that sine is negative and cosine is negative and tangent is positive. So we'll keep that in mind. Okay, there's 2 or 3 ways that you can go about finding cosine of t and tangent of t. One is to use the Pythagorean identity. Sine of t squared plus cosine of t squared equals 1. So if sine of t is negative 3/5, we write negative 3/5 squared plus cosine of t squared equals 1. And so cosine of t squared is equal to 1 minus 9/25. And 1 minus 9/25 is 16/25. So this equation, if it were independent of the setting, has 2 solutions. So cosine of t is positive and negative square root of 16/25, or 4/5. Okay, but in this problem, cosine is negative, so cosine of t is negative 4/5. And then we can find tangent of t if we just divide sine of t by cosine of t. So negative 3/5 divided by negative 4/5 will be positive 3/4. So in this limited space, I'll circle the other 2 quantities that we're supposed to find. Okay, the next problem, we're given that this point is on the unit circle, negative 3/4 and the square root of 7/4. So on the unit circle, the x-coordinate of that point is negative 3/4, and the y-coordinate is the square root of 7/4. And that point corresponds to the real number t. So we know that on the unit circle, from our definitions, the cosine of t is the x-coordinate, negative 3/4. Sine of t is the y-coordinate, square root of 7/4. And whenever we know the value of cosine and sine at some number t, we automatically can easily find the other values. Secant of t is the reciprocal of cosine of t, so this is negative 4/3. Cosecant of t is the reciprocal of sine, so it's 4 divided by the square root of 7. Tangent of t is sine of t divided by cosine of t. So I guess I can write it in some detail. Square root of 7/4 divided by negative 3/4. So this will simplify to negative square root of 7/3. And the cotangent of t, we could just use the fact that it's the reciprocal of tangent of t. So this is negative 3 over the square root of 7. Okay, the next problem, identify the ordered pair on the unit circle that corresponds to the real number t equals 7π/4. Well, if this were on a test, you would at least get partial credit if you wrote that the ordered pair is cosine of 7π/4 for the x-coordinate and sine of 7π/4 for the y-coordinate. That's worth a couple of points. But this involves special angles, so we can determine what the exact values of those are. So let's find where 7 pi over 4 is, which quadrant. So 7 pi over 4, if we wind counterclockwise, we're going to end up in the fourth quadrant. This is just short of 8 pi over 4, so it's not a complete revolution. It's a little bit short. So this is 7 pi over 4, and the reference angle is pi over 4. Okay, in the fourth quadrant, cosine is positive and sine is negative. So we could say, as an intermediate step, the x-coordinate is equal to cosine of pi over 4, and the y-coordinate is negative sine of pi over 4. But we know what those are. Cosine of pi over 4 is the square root of 2 over 2, and negative sine of pi over 4 is negative square root of 2 over 2. Okay, next page. Find the reference angle and quadrant for the angle that measures negative 8 pi over 3, then evaluate the 6 trigonometric functions. Okay, negative 8 pi over 3. Notice, if you want to look at negative 8 pi over 3, that's equal to negative 6 pi over 3 minus 2 pi over 3. Negative 6 pi over 3 is negative 2 pi, so that just represents one revolution in the clockwise direction. And then it goes a little bit further. So this is going to end up where? So let's do one complete revolution clockwise. That's represented by negative 6 pi over 3. And then minus 2 pi over 3 more. So minus 2 pi over 3 more will be in the third quadrant. So negative 8 pi over 3. And we're pi over 3 radians from this terminal side to the negative x-axis. So the reference angle is pi over 3. Another way to do the same thing, if you begin with negative 8 pi over 3 and then add 2 pi, I'll write it as 6 pi over 3, we have negative 2 pi over 3. And then if you add 2 pi to that, negative 2 pi over 3 plus 6 pi over 3, we get 4 pi over 3. Okay, so the idea is the angle 4 pi over 3 is coterminal with negative 8 pi over 3. And you can, I won't draw it in, I'll just go through the motions. 4 pi over 3 will end up in the same place. Okay, so we can write down the 6 trig functions. Sine of negative 8 pi over 3 equals something cosine of negative 8 pi over 3. And then tangent of negative 8 pi over 3. And once we know those, we can just use the reciprocals to find the other ones. So sine of negative 8 pi over 3, since this angle is in the third quadrant, this is going to be the negative of sine of pi over 3, because sine is negative in that quadrant. So this is negative square root of 3 over 2. Cosine is also negative in the third quadrant. So this is the negative of cosine of pi over 3. So this is negative 1/2. We know that tangent is positive in the third quadrant, and it's sine divided by cosine, and we're just going to get the square root of 3. Okay, so we might as well write down the other 3 functions. Cosecant of negative 8 pi over 3. That's the reciprocal of sine of negative 8 pi over 3, so negative 2 over the square root of 3. Secant of negative 8 pi over 3 is the reciprocal of cosine, so that's negative 2. And I'll squeeze in cotangent of negative 8 pi over 3. That's the reciprocal of tangent of negative 8 pi over 3, so that's 1 over the square root of 3. So we got all 6 in there. Okay, the next exercise, if cosine of t is equal to 1/2, then cosine of negative t equals 1/2, because cosine of negative t equals cosine of t. This is due to the fact that the cosine function is even. If sine of t equals the square root of 3 over 2, then sine of negative t is equal to negative square root of 3 over 2. This is because sine is an odd function. Sine of negative t equals the negative of sine of t. Okay, evaluate secant of 5 pi over 3. That's the reciprocal of cosine of 5 pi over 3. So if we can find cosine of 5 pi over 3, then we'll just take the reciprocal. So cosine of pi over 3, well, it's pi over 3 short of 2 pi. So counterclockwise, and we stop in the fourth quadrant. So this is 5 pi over 3. The reference angle is pi over 3. Okay, and we know that cosine of pi over 3 is 1/2. So that's equal to cosine of 5 pi over 3 because cosine is positive in the fourth quadrant. Okay, so secant of 5 pi over 3 is equal to the reciprocal of 1/2, or 2. Okay, the next problem, simplify tangent of t times cosecant of t. Well, we know that tangent of t is sine of t divided by cosine of t, and cosecant of t is 1 over sine of t. The sine of t's cancel, so we have 1 over cosine of t. But we'll rewrite this as secant of t. Okay, so the simplest way to write tangent of t times cosecant of t is to write it as secant of t. Okay, the next problem, cotangent of t is equal to 4/3, and t is in the third quadrant. Okay, so find all of the other trigonometric functions. Well, the hint is use one or more of the Pythagorean identities. So sine of t squared plus cosine of t squared equals 1. If we divide all of those by sine of t squared, we get 1 plus cotangent of t squared equals cosecant of t squared. So if I use this identity, because we're given that cotangent of t is 4/3, then I can write 1 plus 4/3 squared equals cosecant of t squared. So 1 plus 16/9, which is 25/9. That's equal to cosecant of t squared. So cosecant of t squared is using the square root method. We get positive and negative 5/3. Okay, well, the t value is in the third quadrant, and cosecant is negative, so cosecant of t is negative 5/3. We can also write down what sine of t is, because that's the reciprocal of cosecant. So sine of t is negative 3/5. And I'll just write down what cosecant is again, negative 5/3. So now what we have to do is, if we can find out what cosine of t is, then we'll be able to find all of the other ones. So what do we do now? Well, there's another. Why don't we just use this identity right here, the original one that I wrote? If sine of t is negative 3/5, then we square negative 3/5. And then plus cosine of t squared equals 1. So cosine of t squared equals 1 minus 9/25, which is 16/25. And in the third quadrant, cosine is negative, so I'll just cut to the chase. Cosine of t is the negative square root of 16/25, or negative 4/5. And so secant of t is the reciprocal of cosine, so negative 5/4. And the last one, tangent of t, that's the reciprocal of cotangent, so it's 3/4. Okay, so it was kind of sloppy, but we got it done. We found all 6. The first one was given, and then we found the other 5. Okay, we're out of time. So join the Zoom meeting on Monday a few minutes before 11 o'clock so that you could start test 1 a little bit early. And then after test 1, at about 11:50, we'll have a class period, and we'll cover the first part of section 8.3. But that's all for today.